Okay, welcome to this live stream. We are talking about calculus and algebra functionality for the upcoming version of Wolfram language. And this is the first I'm seeing of this. I don't know. Roger, can you give me a sense of how big this thing is?
Yeah, so let me give you a backdrop to this. So in the early days of special functions, we were sort of happy with having numerical evaluation. And getting numerical evaluation over the whole complex plane was yet another sort of big thing. Then very quickly, I think people here, this before my time, people realized you need a few properties like derivative. And a little bit later, an asymptotic series. But over time, we've accumulated many more properties. And ultimately, what this gives us is a way to think about functions as function classes. Because what we can't have, for instance, this is useful in its own right. So for instance, students and others want to find out if a function is injective. There's a lot of Wolfram alpha traffic for that. But also for solvers. The way you write solvers is you often need to check a certain property, in which case you can use a whole bank of theorem, a whole network of theorems are true for that class of functions. And now you can have algorithms that go that way. Now these things do that for you instead of you trying to ad hoc do that, and they do it efficiently. And some of them is extremely efficient. And so this is a way to get to function classes and function properties. And if we go there, there's a guide page for it. It's easy to click from. There's one thing here that you're going to get hung up on right away, which is the C at the end. And the thing is that we can't have Q at the end because Q functions are liars in my book. Q functions has to return true or false. But often you have parameters there, and you can return a Boolean statement that when those parameters gets instantiated can become true or false. But just returning true or false for something that depends on a parameter is always a lie. Well, often a lie.
Look, so, I think we'd be better off calling it test, injective function test or something.
Then C. But then, so we're going to introduce this, I wish we'd had it 10 years ago, this convention, because right now we've done like no ending for a lot of functions that does this. But I don't know that we want test, because test has many meanings. Hypothesis test, for instance.
This convention isn't going to make it, but we can come up with something. Okay. Let's go. This is going to be a long and complicated review.
Possibly. I mean, it's not. I mean, these are slightly sophisticated, but I also expect us to do more than 1 hour. Okay. This just gives you the overview, and you sort of see what you think is complicated or what needs more time and stuff.
What is this? What is this? Function properties?
Yeah, that's the name of the guide page.
Am I going to be able to get to these functions from here?
Yeah. I just didn't make them hyperlinks.
Doesn't look like it.
No, I mean, I just didn't make them hyperlinks, but just mark that and then go to the Docker tools and click on that dot, and you can go directly to it. That dot thing?
This thing here?
Yeah, once it's selected. Now, this is not new.
And we already have.
Yes, but it should be on this page. You see what I'm saying? It's a function property.
Yeah.
Okay. So our support for special functions is significantly deeper than just numerical evaluation. In fact, numerical evaluation alone makes them close to useless from a symbolic point of view.
So how far can injective function get?
What do you mean by that?
Well, I mean, if I give it a complicated thing here, I see.
It can get pretty far. I mean, the whole point here, this is not some like table lookup for special functions.
Does it work with discrete functions as well?
Well, depends on how you define discrete functions.
Functions over the integers.
That's not going to work for this guy. No.
Why? Why?
Sorry?
I said why?
Because it's not implemented.
Okay, but it's conceptually can work.
Conceptually, it could work, yes. But the
Okay.
two domains that are supported are reals and complexes.
Well, it's an interesting piece of functionality for sure.
This particular one, you know, apart from us having those
this
on the
font
to-do
is
list,
just wrong. That font for that if is just wrong. We've been through this several times before.
that's the typesetting for conditional expression. So that
I know it's wrong.
Yes. Okay. Could you just take that the vendor as a bug report for conditional expression?
Yes, I did.
I mean, this is like the third time I pointed out the same thing. Okay. In any case. All right.
And I think that the applications are getting in place. I think that these applications is where you learn why you care. You don't learn why you care so much in the notes or in the scope.
I think this should be called function injectivity, function continuity, function analyticity. I admit I don't know what the noun form of meromorphic is.
Meromorphicity? Never heard that.
No, nor have I. But I think so. Function injectivity would return
true, false, typically, or the conditional answer.
Yeah, test is the wrong name for this.
Yeah.
I mean, I kind of like going with function domain, function range, function injectivity, function sign, function convexity. Seems to make sense to me.
Those are a little bit different. It's those three there, sign, monotonicity, convexity. So we have this problem. There are basically four functions that you want for sign. You want to know, so we have four functions for numbers. So we have positive, non-negative, negative, non-positive. So we have four of them. So in principle, there are four of those for functions too. Same thing goes with monotonicity. You have increasing, decreasing, strictly increasing, strictly decreasing.
Yes.
And you have four for convexity as well. So these ones return.
Well, what about multivariate convexity? Multivariate any of these?
Well, the monotonicity is not defined, but they
why?
Because
it's defined for one variable.
Sorry?
It's defined for any particular variable.
Yeah, for one variable, then it's not multivariate.
No, I understand, but multivariate function, well, okay. All right.
Okay, but the other two work multivariate.
Okay, so you've got an option here. How does that relate to intervals? So if you support that here, you've got to support that for intervals.
No, I don't have to.
Why?
Why do you say that?
Because it's the same question. Same
no,
issue.
It's not the same issue. Intervals are made for interval computation, meaning, for. Yeah. I know that you've had this debate elsewhere. How are we going to kind of represent open-closed type intervals? But this doesn't necessitate solving your interval problem here because we're solving it here.
No, I understand that, but you need something which is going to be usable elsewhere.
Why?
Because we don't want to have two concepts here. Oh, that's interesting. IC points out that there is a resource function in WFR called function jectivity. Have you guys looked at that?
No.
Why not?
We've not. I don't know. We wrote this several years ago. So That was probably long before it existed. So no, we have not looked at that.
Okay, let me go and look at it.
Sure.
Oh, it came from the Wolfram Alpha math team.
Well, this was a request from the Wolfram Alpha team to do this injective, surjective, bijective.
Okay.
And I think they put it in here as a placeholder for
Okay, fine.
Wayne.
Okay. Okay. But I kind of agree that having the explicit complete names is better rather than putting it all in one function.
Oh, yeah.
Sandra is immediately asking on our live stream, what's that C thing? The C thing isn't making it.
Conditional means conditional.
But it isn't going to make it, so.
Yeah, I think it's a convention we should have across the system, not only here, but across the system.
Yeah, but I don't think we're going to be able to do that. I mean, I think that this is a, it's a nice thing to say, but I mean, I think function surjectivity.
No, that avoids it in a different way. So that solves it, but it won't solve. This problem will come up repeatedly. It has come up many times in the past.
No, I understand.
I
understand. The issue is things which are Qs but not Qs.
Yes.
And how strictly do we?
We cannot use Q. We cannot use Q. Q is a liar function. It works great for structural things. It works terrible for things with parameters and conditions.
I don't think you should say that so quickly. I think it's one of these things where I think we should look at what Q functions exist. When we've done this, which I know we have done, even though we shouldn't have done it, of having them not be definitive true or false. I think we should separately, somebody should look at all Q functions and try and figure this out and see whether there's a nice way to generalize this. Okay, I don't know what it is right now, but a general way to generalize it, so to speak.
Mm-hmm.
Okay, so which functions here? So so what we're looking here at is monotonicity. So this is right. So function monotonicity would go along. Function surjectivity is just true, false, or a condition, right?
Yeah, that's what I was saying, that those guys behave a little different because they effectively return what's like a sign, basically, this 3-valued logic or 4-valued.
Which do the monotonicity and so on.
Yeah, these guys. Because you can have, it can be positive, negative, or both. I'm sorry, sort of non-positive, non-negative, or both.
Yes, I understand. I kind of agree with this. I think that's a reasonable thing to do. And it agrees with how the SIGN function works for numbers, right? It's going to do the same thing. If it's a constant function, it'll give the same result as the sign function on the number.
Right.
Okay. But now, okay, I don't really like the name strictness. I think we need to understand what that's going to be elsewhere so that we can at least reuse that name elsewhere.
Sure. No, I'm not super fond of it either. I was trying to come up with other names for it. But...
All right. Okay. So we'll come back to that in a minute. Nick on our live stream suggests generate conditions for Q functions. I think that's a separate. Who is making notes here? That's a separate meeting that we need about.
Yes, I'm making them. Yes.
Okay. Fine. All right.
It's not always going to be. Yeah. I don't. Okay. It's not always going to be conditional. Sometimes
I know. On our live stream is suggesting a curried form, but I don't think it's a good idea. I don't think it's sensible. I think these concepts of surjectivity and so on are so
Yeah.
I mean,
look, it's elementary. I mean, it comes up super early.
right. So let's say function sine of a times e to the x with respect to x, right? Is that what I'm saying?
Mhm.
Okay, beautiful. Except for the typesetting, which drives me crazy.
Right.
Okay. All right. So down here, these are function continuous, function analytic, function. I think we should just say function meromorphic. Oh no, that would be function continuity, right?
Devendra, are you taking notes for the new names, or?
Yes, I am.
Thanks.
I don't know what the right function meromorphicity. I don't know what the noun form of meromorphic is.
I think it's meromorphicity. Like your holomorphicity, so your meromorphicity. I think.
Okay. It's a bit weird. It's not terrible, actually. It's really not terrible. Okay, so are you telling me things about, okay, so let's say I say your function convexity okay, but so now if I say function convexity x, how do I give a condition?
Sine x, comma, condition.
Sine x in a brace like this.
Yeah, comma, condition. So it's concave.
No, that's right. I'm just thinking about the, but now, why is this saying indeterminate? Because it can be all anything as opposed to it being, what if it could be?
There is any linear function is both convex and concave, so that returns 0 if it's both. Okay, if it's neither, it's indeterminate. It's neither convex nor concave, which is true for sine. It's a sine in general.
So basically, this is the sine of the second derivative, basically.
Yeah. If it has a derivative, yeah.
Okay. So I see. So this is the sine of the function itself, the sine of its first derivative, the sine of its second derivative.
Right.
In the first approximation.
Yep.
It's reasonable enough.
And they're strongly connected. If you integrate a positive function, you get a strictly increasing function.
Yes, indeed.
If you integrate a strictly increasing function, you get a strictly convex function.
I know.
Okay.
Good.
But it works in general. I mean, that hierarchy is a good hierarchy.
That's okay. So the issue here is strictness, strict condition. See, the question is there are two kinds of things that could be strict. There's a question here about. Yeah, that's a good question from Sander. Why is this only giving this case? And says kind of you're out of luck for the other case. I guess that's what we do in general. We give a condition, but we don't give all the different cases unless you ask for them, right?
Yeah.
So how can I ask for them in this case?
I don't know if you can ask for them, and it's not true that you can. In general, our algorithms in general never give you the option to return all. There's a few exceptions in integrate where we give all, but that also has exponential blow up of cases happening, of course.
Nice enough. Okay, I'm still trying to understand the strictness. So the issue is the condition that you are implying, the monotonicity condition is what's strict. It's not that you're interpreting the input in a strict way. It is that the condition being applied is a strict condition.
Yeah, they're all given as inequalities, and those can turn into strict inequalities. And they're usually used also, like you say, is this strictly positive or just positive?
Yeah, I understand.
Okay, is this strictly increasing or just increasing? Is this strictly convex or just convex?
Strict enforcement of condition. Condition. That's really weird. For these asking, is this analogous to find instance? What is the analogy with find instance here? By the way, could you report, I don't know, why is find instance giving completely stupid search results here? Devendra, those are 2 bugs to report. That does this. Can you report that bug? Did you understand? Devendra?
I'm taking notes as well. I've got it. I'll tell Devin and the search team about it.
Okay. The other thing is, when I was in this state here, what happened to Devendra? Devendra is...
I'm here. Sorry, I just moved for a minute. Yeah.
Okay. In any case, all right. So we got a name there that we got to deal with. Is what? Oh my gosh.
Strict
also,
definition.
that raft, I'm sorry, another bug not fixed here is that this raft is disappearing immediately. Do you see that? Who was the one taking notes? Is it
Yes.
Scott? Oh, okay. Do you understand? This is the same front-end bug that we've seen for like 3 weeks.
Okay, yes.
You call that cell a raft?
No, I call the attached cell a raft.
Is it your name, or is it is that a general name? Or?
No, I made it up.
Okay. Okay.
It's a partly silly name, but it's a name that the UX team understands.
Okay. Yes.
It's a floating raft.
Okay. Okay.
That is also used for help. You know.
Yes.
Okay.
It's like using the strict definition of the property.
Yes. Okay.
But I never got what the person thought that how it relates to find instance. It's
because the point is that that you're not finding all not finding all conditions. You're simply finding an example of an answer with a
okay. So in that sense, it's not quite instance find truly an instance. This finds a generic.
Something that tries to be generic, but the genericity might be only half of the complex plane or something.
That's right.
But it's not a set of measure 0 in the complex plane, and it's
it's not like find instance. It truly finds something a measure 0. It finds a point, an instance.
Right. Okay. Anyway, so we've got one issue here is with this strictness name, but I think in terms of now, I wanted to look at so convexity. I like this plus minus. I think you should say in this documentation here, convex +1, concave -1, or whatever it is. Just put it right in there.
Yes. Okay.
Convex +1, concave -1. Increasing
+1,
decreasing -1 type thing. It's really simple. Or we could just put convex : +1, concave : -1, comma ... Okay, there's a question from Sander here on what does something do?
So this is not a new function. So what's the I don't know what the question
is. The question is, what is that? The reason that says 0 is the function is not periodic with any non-zero period, right?
That's right.
Because eventually this function will be, I mean, it's a non-commensurate thingy-dingy.
Yes.
Oh my gosh, this bug is driving me crazy. Beautiful. Okay. All right. Now, any of these things, they just return true, false, right? Function continuity, functionality, and so on.
Right. With possible conditions, right? So.
Yep. Okay. So the only issue, so do they have any weird options?
No. Double check, but I'm pretty sure they don't. It only came up with those guys. Yeah, nothing weird. Just standard stuff.
Look, I would say of these things, Sandra's saying, why is the period infinity? Why is it zero, not infinity?
Yeah, you can argue that. And people have argued that and come to both conclusions.
Yeah, I can see that. All right, but so
this also works better with complex periods because we can very much have complex periods. And what does infinity mean in that case?
How do we get a complex period here?
Take something.
Will that work?
Yeah, but you need to take something with an actual complex period, like, you know, like some elliptic function or something. Jacobi's.
SN, yeah, probably.
Yeah, I know. How many arguments does Jacobi have?
2.
I can never remember.
Use x comma k, and the k might have been numeric. X probably.
Nice. Nice. Yep. But now, I don't understand why that's coming out as a list as opposed to a complex number.
It has 2 periods.
But aren't its 2 periods just in the real and complex, real and imaginary directions?
No. I mean, the ones that we give here, yes.
I'm confused. So if I make this pi over 3 plus I, for example. Oh, I see. So when you give a complex, when you say it's over the complexes, what you get back is a list. Is it always a pair?
Yes, but you also have multivariate, which returns, you know, a list. You know, so this works just fine for multivariate. You know, n variables too.
So does function convexity work for multivariate also?
Yes.
So if I say function convexity.
And that's actually where we need it, because we use this in our convex optimization to classify and transform.
Okay, why does it say that?
Because it's not convex.
But it's a saddle.
So it's not convex. Yeah,
I see. But so I see. But so is there not a characterization of the saddle that is useful? I mean, in other words, a generalization of convexity for this case.
What I mean, what kind of generalization?
I don't know. I mean, isn't that what all these Hessian-y things are telling you?
Well, this one just says that it. I mean, if you look at the Hessian of this, you will see that it's in indefinite form. It's not positive or negative definite.
Okay. Well, I'm not sure I know what I'm talking about, but it's like the principal components somehow.
Yeah, but you're going to see that it has one positive eigenvalue and one negative.
No, I understand that, but to be able to say, in a sense, what are the eigenvalues, rather than just, oh, is it convex altogether or not? Do they all agree, or I've got 2 positive eigenvalues and 3 negative eigenvalues, for instance. Wouldn't that not be a useful thing to?
That's a different function, though. That's not.
No, okay, fair enough. Okay, does it have a name?
I mean, this is what you look at these catastrophe analysis and stuff. I mean, that's where you. But that's not going in this direction.
Fair enough. Okay. All right, let's go on looking at these here. Okay, so we've got condition strictness. I'm not sure I'm totally like that name, but it's better than just strictness in my view.
I was looking for something a little bit less generic like that.
And it's not fantastic, but I think let's go with that for the time being, but I think we want to talk about it again.
These two are amazing functions. So what they will do is they will tell you all the things. Yeah. We've had them. I wrote versions of this long time ago, but we've now made them production. And so we've used them inside. So for instance, when you plot the function and it can figure out where the discontinuities are or the singularities are, that's what's being used under the hood.
So these are really giving conditions like reduce.
Yes. And they can be fairly complicated. Well, you have one example right there that's fairly complicated at the end.
Yeah, I understand. I'm just concerned about the names, the name, function singularities, because it suggests that boom, 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 it's just values, which could be its own function.
Oh, but you know, function singularities can be curves. When you multivariate, you can have singularity surfaces, singularity curves. Absolutely.
No, I realize that, but I see. So you think the singularities.
And that's something we found that the theories. I mean, I wish the theory was farther ahead here, but we really need it for convergence and all kinds of other properties.
Right, but so if I want to take this thing and I want to just get numbers out of it for the univariate case, if it has numbers, I mean, it could have. I mean, what happens if the
We'll take something simple, like take gamma. Okay, well there you have 10 is something simple there. Okay.
No, I'm going to take one of the more complicated cases. I'm going to take sine 1 over x. Okay. And now how do I know that that's an essential singularity?
That's further analysis. That's in the series expansion. You have to do further analysis to classify it.
I understand that, but what I'm asking is there a function that tells me that?
No. There's no shrink wrap function that tells you that at this point.
What are we going to call it if we have it? Function singularity analysis?
I don't know.
I mean, because what it would naturally return is an association saying essential singularities arrow blah.
That's
poles arrow blah. Does that make sense?
I don't know. I think those concepts seem to degenerate in the multivariate case. They don't seem to work anymore.
Yeah, they certainly do. Right.
So
well, maybe that's just a WFR level function. Okay.
What we've discussed, which we can't do now. So this function is super fast. You know, for in a fairly complex expression, it will actually return in microseconds, not milliseconds, microseconds.
Which function?
This one, function singularities. It's amazing. What?
I'm looking at polynomial Q. I'm on to the next item. Oh my God, what is this? What is polynomial expression Q?
Yeah, I wanted to have a longer discussion, sort of. So this is the problem. Adam needs to be here in this discussion for it to kind of make a lot of sense. I don't.
Okay, all right, fine. But let's put it on a different agenda then.
Yeah, let's do that. And he's on vacation, unfortunately, now, so it's.
Okay, but roughly, this is some piece of hackery to fix up another piece of hackery.
Yeah.
Well, we should fix it some other way.
Well, that was where I was going down.
Okay.
That's
fine.
why I said revisit.
Okay. Oh, I see. Okay, fine. All right. Is that it for the discussion of those things here?
It is, yeah. For the function
Sandra is
properties.
asking for an n function singularities for the real points rather than the equalities. Yeah, I guess I'm asking the question, if I get out something like this,
You have to
now I
solve
want
for
to
it.
yeah, but how do I just get a list of numbers within a certain range? If I say, take this
You
thing,
solve it within that range. Okay.
and solve %18, now what?
Whether you have to give the range over which you want it.
Okay, so I'm saying %18, comma, 0 less than x less than 20.
For instance, except it has none there. So that was a short
That's
list.
the gamma function. Yeah, sorry. Oh God, this bug is driving me crazy with that. Okay, and I can say n solve values here.
No. What's that?
Why not?
Doesn't exist.
Yeah, I've never heard of that.
We should have it and do the obvious thing. I mean, we have that for d-solve values, right?
We do.
Yes, we do.
This should exist for the exact same purpose, right?
It was worse for D-solve because there if you try to.
I understand.
But I'm not arguing with you. I kind of tend to think it should exist too.
Let's try and make it solve values and solve values.
Okay.
Yeah.
Okay. So basically what you say is n solve values, function singularities, blah, blah, blah. And if this thing is bounded, so if I say here, the gamma function minus 20 What?
It doesn't take a condition, I think.
It should.
Well, it will just spit it back out again.
I know it will.
Which is kind of okay, I guess, for workflows.
Yeah, I think it's a very good thing for it to do. I don't think it should complain. I think it should just come back right back out again.
Mm-hmm.
But I mean, it could be, it won't be exactly the same. It'll be an ANDed thing, right?
Yeah, it will.
Should work. Okay, let us keep going. Jacobi epsilon. I have never heard of that. Jacobi ZN. We are getting exotic here.
This is all triggered by a bunch of bug reports on our elliptic functions, several of them from you, or some of them from you.
Not directly from me, surely.
Maybe not. You might be right. Okay.
They may be Gosperisms.
Yes, most likely. This should all be, 100% cleaned bugs,
Good.
but that meant a complete re-implementation of those elliptic functions.
Wow.
So, elliptic K, E, F, pi. And as a side benefit, it also got updated in improvements to all these Jacobi functions.
Okay.
And what was I going to say?
Llama functions, are they part of the same? I mean, those are slightly different.
No, it's different. That's related to Hoyne. Okay, so that came out of, since we're now world experts on Hoyne, literally.
Yes.
Llama is just one transformation away from Hoyne.
Yes.
That's why we were able to get Llama now. It was very efficient to do them now.
Have we not had them at all before?
No.
We've had spheroidal harmonics, which is sort of
yes. No, I remember Llama functions. In Abramowitz and Stegen, they're in an obscure part at the back of the book.
Right.
So, are we done with Abramowitz and Stegen now? Is this it? Is this
We're just compiling a DLMF benchmark now to see where we are at with respect to that. Just to and then
we should just check Abramowitz and Stegen. I mean,
no, we should, but we're doing some 10 different sources to see where we're at now with special functions, generally speaking.
It's only been 30 years. We're finally there. We're finally
Yeah. But we're actually measuring it now, Stephen. We're sort of checking and measuring. And
actually, the one other thing that they have in Ronson-Stegen, if I remember correctly, and it's been rather a long time since I actually looked at it, but they have some tables for numerical analysis in the back that are weights for Gaussian quadrature and things like that, which I think if we don't have those in the function repository, we should put them there. I mean, I really don't think anybody needs weights for Gaussian quadrature as primary things because they are, just inside the algorithm.
Right.
But we probably should expose that in the function repository. Can we, Devendra, could you make a note of that?
Yes.
Maybe Mark could, I know Mark has developed functions, internal functions that do that, but nowadays we can put them in the function repository and document them.
Okay.
Yeah.
Actually, that QPOC hammer was another Gosperism.
Right, I know he's been a QPOC hammer enthusiast he's been hammering on that function for years.
You know, we hired him to try to have him implement it, which failed.
Yes, I know.
Okay.
That was a long time ago.
But now he's working on the outside and finding problems, which is fine. Things have progressed.
Yes. That's interesting. So there's a question from Nick here. Reduce. Wow, that's going to be a challenging thing. If we say here, let me show you this one. That's going to be challenging. Interesting, but challenging.
Yeah. So, but he's on to something. So we are gradually getting into sort of a kind of a type system, but not really. But I mean, it is it. So one thing that we are introducing for sure is matrix classes more substantially because they're needed in optimization modeling. But we will need these function classes eventually.
The symmetric matrix type thing and so on. I mean, this is in a sense the lie of type systems. I mean, really what you want are conditions on things, and type systems are a pretend way of giving conditions. That is, they're very...
Yes, but they're also sort of a very... Types, I mean, they don't need to be called type systems just because they work on at the structural level.
No, I understand, but the point is that with types, well, I mean, the calculus of types, so to speak, right? The question is this a type? And the answer is, who knows?
It depends on who's defining it. I'm looking at many types is a broad, the things that have been used by compiler writers and language designers is sort of one slice of types. It's not the full slice. There are lots of use in statistics, and even more use in theorem provers. But there are different slices to the whole thing.
By the way, Roger, I don't know if you've been paying attention to it, but I've been doing, as part of this theory of mathematics project, I've been understanding. In fact, we should have this conversation. We've really been exposing things like Lean, their theorem, their theorem inventory. They have about 30,000 theorems in them. And we've been kind of ingesting those and at least understanding at a infrastructural level how all these theorems work. But cool. I think it'd be very interesting to understand, how we make use of those, all those theorems. And right. I mean,
but here is the thing, okay? I mean, here's a very practical thing related to that.
Yeah.
Which is that the thing is that when you say that a function is monotone, there is basically a network of theorems that are now true. You know what I'm saying? It's like a key. Now you can use this result and that result.
Right. Well, okay. I'm sorry, what were you saying for which?
Just pick any one of these properties that we had. Let's say that you say it's a monotone function. You know that for monotone functions, they can be a Stieltjes measure, for instance. They have finite, the bounded variation. There's a whole slew of results that come out as a result of knowing that key. You know what I'm saying?
Yes.
And that's what's good about it. That's how mathematics sort of aggregated and
Well, I
And
mean, but if we look at, for instance, I mean, let's see if I can pull one up. Let's see. I mean, this is MetaMath, which is one of the ones that is not considered as modern as it might be. That's lean. So, I mean, if we take, for example, functional analysis, wherever it is. I don't see functional analysis. Let's see, what should I look at here? Analysis, maybe. Okay, so analytic.
interesting.
So, I mean, we have
we are in fact using a bunch of these closure properties now to get efficient computation of these properties.
Well, I mean, we have this lean link thing which has been built to this. I don't know if you've been paying attention.
Yeah, I mean, I don't think this would be of any use to us for these functions per se. But I'm just saying that we are using closure results of this nature to get, that's why it doesn't just work on individual special functions.
Why would this not
expression.
be useful to us? Why would none of this stuff be useful?
I mean, it's useful to browse to know the result, but calling lean, and this is things that work in microseconds, what we're talking about. Just setting up the call to lean would be a millisecond thing, at least, I'm sure.
Well, I understand, but independent of efficiency, the question is this whole structure here of theorems, right?
Yeah, it might be super interesting. But I don't think we would call on it per se.
No, I understand that. But the question is whether, for example, whether one can basically machine generate code that is provable from these theorems, for instance.
Right. That I'm pretty sure one can.
That will be interesting. Yeah, Ethan is suggesting find theorem and theorem search. Yes, we are well aware of this issue. This issue is a huge can of worms because of
the reason we want these. I'm just saying the sort of where it goes away from special to general functions. Think about our solvers. We have maybe on the order of 100 solvers in calculus and algebra, and they're pretty heavy beasts, each and every one of them.
Mm-hmm.
We have on the order of 300 special functions. Should each one of these solvers know about each and every special function?
Right.
That's 30,000 cases just there.
Right.
Not scalable, not doable.
Yeah, right. Right. No, I understand that you have to bucket them.
Yes. And the bucket are called function classes.
Yes. See, this is an interesting thing for the general sort of theory of abstraction in mathematics. That's an interesting thing because you take 30 cases, right? And then which buckets do you make?
Exactly. And they're clearly history dependent. I mean, there might be real essential things, but the question is like who worked on things and that,
Right. Okay, let me just we really should talk, by the way, Roger, because this is an active subject right now for these, because we're generalizing axiomatic theory to be able to ingest all kinds of stuff. And so it is, this is our moment for figuring out how we take formalized mathematics and connect it to all these other things.
Right.
And
so the next group, holonomic functions, is an old function. We introduced it in version 7. What we're doing now is consumerizing it more. Did I lose you?
Yeah.
We're consumerizing it more. So it's going to have nice typesetting. Unfortunately, that's not, I saw changes already this morning from E-type.
Okay. Hey, listen, with respect to typesetting, could we do a review that includes the typesetting of those conditional results that you had.
Yeah, I think
earlier.
if we have Itai in that discussion, our life would be so much easier because that's where it all goes.
All right, fine. Okay, we have Itai and we need somebody from design in there.
Yeah.
Okay.
And the other thing is that differential root, which sort of covers 70 to 80% of our special functions, is now behaving like a true special function in that it has continuity-based numerical evaluations. I'm sorry,
Yeah,
continuation-based.
cool. Yeah, I understand. Right.
And so guaranteed precision behavior and things like that. And that's in preparation for being able to output these functions massively from lots of different solvers to extend their capabilities.
Mm-hmm. Okay, we are about to need to go to our next meeting, but let's just have a quick preview here. What is cylindrical formula?
It's an optimized. So it's going to take a little bit more discussion, but it's basically an optimized cylindrical decomposition that preserves enough structure that it can be manipulated afterwards. So it leads to
What does
exponential.
cylindrical algebraic decomposition, or what are we calling it? Cylindrical decomposition. What does it return right now?
It returns a Boolean formula.
Is the normal over there?
Yes.
So I see. So this is an unevaluated form of a cylindrical decomposition.
Right. And it's evaluated to a stage, okay? But that stage maintains enough properties that you can, for instance, Boolean combine these things afterward very efficiently.
So how does it relate to regions?
Actually, we came up with this during regions, but it's not an explicit, and it's used inside some region computations.
But isn't it in fact a region?
You could say it's a optimized form for a subclass of the implicit regions.
Yes.
Okay. All right. But I mean, in principle, I could just take one of these cylindrical decompositions or cylindrical formulas, and I could just make a picture of it, couldn't I? With graphics
Yes.
or something.
Yes.
Or region plot.
If it's low enough dimension, yes.
Obviously. Okay. What got done? I mean, okay. So is this hooking up all the?
No. So those two. Okay, that was a little bit too aspirational. It's gonna probably make it till next release, unfortunately. What
is the issue here?
We need a new generalized multivariate form of root objects to do it, and we're not going to be able to pull that off.
Oh, I see. This is maximize, not n maximize.
Right.
Wow.
But it means that this is in my book amazing what we'll be able to do, and I just don't want to talk about it super much yet.
Okay. What got done? What's new in the Laplace transform world?
Right. So, for the inverse, particularly, we have the Bromwich contour integral method and numerical inversion as part of the new inverse Laplace transform. So,
how could you do an inverse Laplace transform without a Bromwich contour?
Well, you can do it for rational case because it's all partial fractions, and you can do it for some other case by table lookup, convolution, shifting, etc. But that's a small bunch of techniques compared to. So basically, if you have an infinite number of poles, you could do nothing in 12.1. Now you can do lots in 12.2.
How do we represent contour integrals in general?
We don't. I mean, actually, integrate has you can give an explicit path, but we're working on prototypes to provide a contour, a more practically usable contour integrate function.
Like named contours.
Yes.
Yes. And so here are some things, and I might get good feedback on the stream here. So often when you do contour integrate, you might integrate, let's say, a meromorphic function. So the only kinds of singularities are poles or something.
Right. And all you care about is the routing of the contour around the poles.
Yes. So you don't want it super exact. You just want to sort of exclude certain things. So you might have an overall contour, but you want to include and exclude points, or maybe even curves if they're discontinuity, like branch cut curves.
Right. So what's our analogy to this? I mean, so basically, this is life with sort of topological or homotopic, you know,
Sort of.
equivalents.
Except what I was saying now is only relevant when you're in the analytic or meromorphic case. If you work on general complex functions, you actually need the exact contour, or it's not defined at all what you integrate.
I understand. But what you're saying is there's a homotopic equivalence class of, of contours that
Yes,
we would like to be
effectively.
able to characterize
They will all
without,
give the same result.
right, but which we'd like to characterize more roughly.
Well, you want to give an easier specification language for the user.
Right, but isn't this analogous to the inside-outside conditions for PDEs and so on? In other words, what you're saying is in a PDE, you say, I want this boundary value, these boundary values inside this region, outside this region, whatever. Isn't that an analogous, somewhat analogous case to the thing I want? I've got this random set of poles in the complex plane.
Yes.
Right.
I want to route this contour. What do I want to say? I want to route this contour. Basically, what you need to say is which poles are inside, which poles are outside.
Yes. That's basically what you want to say.
And what about branch?
That's what I was saying. You want to include poles inside or exclude they outside, and you want to do the same for cuts. Curves. You want to include a curve or exclude a curve. Often you want to exclude a curve if it's a discontinuity.
Although I guess what happens is that there will be implications. If you have routed a contour that isn't a crazy contour and you've excluded certain poles, then poles to the right of that, left of that, whatever it is, will be automatically excluded. That's the case that would be.
Yes. In fact, we use that for numerical inversion as well. We try and include all the poles by taking a large enough contour which covers them, at least enough to get the numerical value right.
So for which? For numerical Laplace transforms or what?
The numerical inverse Laplace transform. So that's a contour integral. But if you're doing purely numerically, then what you want to do is kind of take a contour which is large enough, so to speak, that large radius. And then you get a very nice approximation. So people have worked with these fixed contours, but thanks to all the singularity functions, we can now do it much better in 12.2. So we're already reusing Adam's stuff inside this numerical inversion quite heavily.
The numerical evaluation of these integral transforms is a heavily requested feature, and that's probably function repository items.
Yes,
it's a thing that people want so badly. The Laplace transform is easily the most used integral transform that we have. Again, a lot of requests for upgrades, improvements. So this is it's both a refactoring, which makes it modular and easily extendable for the future, as well as new methods like this Bromwich method.
So is there an n Laplace transform? I don't remember.
No. So the way we've done it right now, there isn't. The way we've done it right now is that if you give a numerical argument to it, it uses the numerical methods.
I see.
Okay. I think if you want an n inverse Laplace transform, what people often write is you get it at a single point. But I think that if we're going to do n versions of all our integral transforms, there's a lot of them, and summation transforms, then I think you want the full function, not just a point.
Right. I'm coming back to this homotopy business because I think it's quite complicated. I mean, isn't this what, all these monodromy groups and all this kind of stuff is for characterizing when, you know what I'm talking about?
Yes.
I mean,
all of that is in a way to deal with contour integration cycles that you're going to integrate along cycles of various kinds.
I just wonder what structure we're going to need to build to represent that stuff in a reasonable way. Because I mean, in a sense, wow.
But it has to be a usable language too. I mean, a user, because people what I've noticed is that there's certain kind of people that think that there is nothing except for analytic functions and poles in the world. There seem to be a lot of, they think that's it. That's not it. If you're going to do a numerical version of that and it integrates, it needs a definite contour. If you give it something non-analytic, which we are fully capable of working with now, at least numerically and visually, Our complex plot makes it easy to understand and start to study these non-analytic, non-meromorphic creaturoids.
Right. Okay. All right. So look, it sounds like we're going to need some follow-up on this, but it'll be fairly brief. A few additional things here. But this is, and we do need to talk about that cylindrical function thing, but it sounds like that needs Adam and so on.
Right.
Okay. Looks like we are good to go here. And we have another meeting that you're probably in, Roger, about visualization, which we will also be live streaming in a couple of minutes.
Yep.
So see you.